What problem does the proposed method aim to solve?
The proposed method aims to investigate and address the optimal model size and number of training tokens for training a transformer language model under a given compute budget. Specifically, the authors aim to determine the scaling laws that dictate how the model size and number of training tokens should scale in order to achieve compute optimal training. By training over 400 language models of varying sizes and training token amounts, the authors establish that for every doubling of model size, the number of training tokens should also be doubled for compute optimal training. The method also aims to replicate and assess the parametric scaling laws proposed by Hoffmann et al., particularly focusing on approach 3, which involves fitting a parametric function to model the final pre-training loss based on the number of model parameters and training tokens. The proposed method ultimately seeks to provide insights into the optimal scaling relationships for training transformer language models efficiently within a given compute budget.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by investigating the optimal model size and number of training tokens for training a transformer language model under a given compute budget. The authors trained over 400 language models, ranging from 70 million to over 16 billion parameters on 5 to 500 billion tokens. They found that for compute optimal training, the model size and number of training tokens should scale at equal rates. For every doubling of model size, the number of training tokens should also be doubled. They used 3 different methods to estimate the compute optimal frontier: training models of fixed sizes on varying numbers of tokens, training models of varying sizes targeting fixed compute budgets, and fitting a parametric model of the loss as a function of model size and training tokens. The key result was that the model size and the number of training tokens should be scaled equally. They then attempted to replicate approach 3 by fitting a parametric function to model the final pre-training loss. Their analysis revealed substantial differences from the fit reported in a previous study by Hoffmann et al. They conducted a test to determine the significance of the differences between their estimates and Hoffmann et al.'s estimates, which showed that the differences were extremely statistically significant. The proposed method involved fitting a parametric scaling law to the data, testing the significance of the differences in estimates, and evaluating the fit of the estimated scaling law to the data.
What are the theoretical or practical benefits of using the proposed method?
The theoretical and practical benefits of using the proposed method lie in the accurate determination of optimal model size and number of training tokens for training a transformer language model within a given compute budget. The method, known as the Chinchilla Scaling laws, establishes that for compute optimal training, the model size and number of training tokens should scale at equal rates. For every doubling of model size, the number of training tokens should also be doubled. This approach provides a systematic way to ensure efficient resource allocation in training language models, leading to improved performance without unnecessary computational overhead. Additionally, by replicating and scrutinizing the findings of previous studies, such as Hoffmann et al., the proposed method contributes to the advancement of scientific knowledge in neural scaling laws and sheds light on the parametric form of scaling laws for dense transformers. The method also highlights the importance of robust statistical procedures in estimating model parameters and confidence intervals, ensuring the reliability and reproducibility of research findings in the field of language modeling. Ultimately, by offering a more accurate and reliable framework for determining optimal scaling policies, the proposed method can guide the development of more efficient and effective language models, benefiting both researchers and practitioners in the field of natural language processing.
How was the method validated or tested?
The method was validated or tested by comparing the estimated model from the paper with the model obtained through their own analysis. They conducted a likelihood ratio test to determine if Hoffmann et al.'s estimated scaling law fit the data as well as their own fit. The test resulted in a rejection of the hypothesis that Hoffmann et al.'s estimate performed as well as their fit, with a p-value of less than 10^-135. Additionally, they examined the residuals of the fitted scaling law and found that their estimated scaling law had residuals tightly concentrated around 0, indicating a better fit. They also used a Kolmogorov-Smirnov test to reject the equality of the distribution of loss values, further confirming the discrepancy between the two models. Furthermore, they conducted a test based on observation differences between their estimates and Hoffmann et al.'s estimates, which showed that the differences were statistically significant, with small p-values indicating substantial deviations in parameter estimates.
What specific results were achieved with this new method?
The specific results achieved with the new method include the reconstruction of data from Hoffmann et al.'s Figure 4, the fitting of a parametric scaling law to the reconstructed data, and the comparison of the estimated model with Hoffmann et al.'s model. The new method revealed substantial differences in the estimated scaling law parameters, particularly in the values of E and beta, which were found to be highly statistically significant. The analysis showed that the estimated model based on the new method provided a substantially better fit to the data, compared to Hoffmann et al.'s estimated scaling law. Additionally, the new method highlighted the implausibly narrow confidence intervals reported by Hoffmann et al., indicating that their reported confidence intervals were much tighter than what would be expected given the number of data points available. Furthermore, the new method demonstrated inconsistencies between Hoffmann et al.'s estimated scaling policy and the scaling recommendations from other approaches, suggesting potential issues with the accuracy of their parameter estimates. Overall, the new method provided critical insights into the limitations and discrepancies in Hoffmann et al.'s reported results, emphasizing the importance of further investigation and clarification in this area of research.
What are the limitations or drawbacks of the proposed method?
The limitations or drawbacks of the proposed method include the poor fit of Hoffmann et al.'s estimated Chinchilla scaling law to the reconstructed data, even after excluding outlier models and considering potential noise in data reconstruction. Additionally, the implausibly narrow confidence intervals reported by Hoffmann et al. For parameters A and B raise concerns about the validity of their estimates, especially considering the relatively small number of data points they likely had available, around 400. The estimated scaling policy derived from Hoffmann et al.'s approach 3 is inconsistent with their other approaches and the 20 tokens per parameter rule of thumb they used in practice, indicating discrepancies in their findings. These inconsistencies suggest a need for further investigation and clarification to ensure the robustness and reproducibility of the research.